something that we've introduced in some parts earlier in the semester. We're going to look at phase change, and we're going to look at the Clausius-Clepayron equation. In this set of slides, I'm going to go through some things in detail, but lots of the derivations you'll need to work through by hand, so I'll just give you the high points of those. Anyway, so we'll do an introduction. We'll introduce the idea of a first-order phase change. We'll introduce the equation for phase changes, and then we'll look at some higher-order phase changes. Basically, we're going to be interested in the three normal phases of matter: solid, liquid, and gas, and we'll be considering what happens as you move between those phases. Starting out from a solid, you have to add heat, and to convert a solid to a liquid, you have to add the latent heat of fusion. In moving from a liquid to a vapor, you add the liquid heat of vaporization, and we have introduced those ideas before. We can get the basic idea using our relationship between entropy and heat transfer for a reversible process. And what we'll do is we'll work with molar quantities, so we'll use little s and little l for those, and we'll use a lowercase g for the molar Gibbs free energy. But anyway, using the relationship between entropy and heat transfer, we can say that T multiplied by the change in entropy is equal to the latent heat. And then we can look at both the Gibbs free energy and its first derivatives, one of which is equal to volume and one of which is equal to entropy. And we can see what happens across the phase change. And it turns out that the simplest phase changes are called first-order phase changes, where the Gibbs free energy itself is continuous across the boundary, but its first derivatives, volume and entropy, are not. So this just shows you the Gibbs free energy across the boundary, where we have an initial phase and a final phase, and we're just looking at the Gibbs function. If we look at a graph of entropy and the partial derivative on the ordinate axis, there is the entropy. Then there's a discontinuity in the entropy. And also, there's a discontinuity in the volume. And again, dg by dp evaluated at constant temperature is the definition of the volume. So other quantities, other related quantities also show some interesting behavior. If we remember the definition of heat capacity, we can relate, we can look at the heat capacity at constant pressure. Then we can use the relationship between heat transfer and entropy change. And we can see that we can define heat capacity in terms of the change in entropy. We've done that before. And if we look at what happens during the phase change, the pressures are constant. dT is equal to 0 because the temperature doesn't change while the phase is changing, and that means that the heat capacity at constant pressure becomes infinite during the phase change. This is only true when both of the phases are present. Here's a graph showing what goes on. We can do similar things with the volume expansivity and the isothermal compressibility. And the next thing I'm going to do is derive the Clausius-Clepayron equation. What we basically do is we write entropy as a function of volume and temperature. We're again looking at the molar entropy. And since temperature is constant during the phase change, that simplifies for us. So we only have the first term surviving. And we can use the Maxwell relation that comes from Helmholtz free energy to rewrite that expression. And there you see we have the Clausius-Clepayron equation. We can write it in terms of the molar masses, or also, if you like, the we can use unit mass quantities. We can also write it back in terms of general expressions. But anyway, the point is the governing equation, the Clausius-Clepayron equation at the bottom of that page. And I also then go ahead and do a more rigorous derivation of the Clausius-Clepayron equation, basically arrived at from equating the molar Gibbs free energies, and work through the details of that, and the result follows as before. You can extend these ideas to higher orders. You can look at the second derivatives. It turns out, though, that although there are theories of higher order phase changes, there aren't very many first order phase changes. Sorry, there aren't many phase changes above the first order. There are some mixed ones where you see different orders of derivatives having discontinuities, but mostly the idea that all phase changes can be ascribed to different orders of discontinuities in the Gibbs function is now no longer used, but we still use the idea of the first order phase change. I'll go ahead and work some examples for you on this, showing the pressure effect on both the melting point and the boiling point of a material. So I'll conclude at this point. You should take some time working through these equations, and you should also look at the examples, and I'll assign a few for you to work. But that's the overview of phase changes and this particular equation.